Hey guys, so today we're going to be talking about the average rate of change over an interval. So go ahead and pause the video. I'm going to zoom out so that you can see. Pause the video and set up your notes outline. And when you're ready, go ahead and press play again. Okay, so today we are talking about average rate of change over an interval. So rate of change. What are some rates that we know? Some commonly used rates. Yes, sir? Prices. A price of something is a rate. Speed is the most commonly used rate that we've got. Now, what's special about rates? They're ratios. Yeah, like speed is a ratio of miles per hour. So it's a ratio. When we're looking for average rate of change when given graphs, how many of you have heard of slope before? So hopefully my 8th graders remember slope from last year because you did stuff with slope last year. Now, when we're finding, again, key word here though is average rate of change. Okay, because for those of you who've done slope before, it's all been with something that is linear. Okay, a perfectly straight line which has a constant rate of change. It is constantly moving at the same rate. Well, given these two graphs that we have here, these are definitely not constant. So when we're looking for the average rate of change, it's amongst a given interval. So from the first one says from -1 to 1. So from -1 to 1. Now they were super nice and they already went and identified the points that we're at when x is a -1 and when x is 1. So when we're looking for the average rates of change, we're really looking for the slope. Does anybody remember what the phrase is to find slope, Jack? Rise over run. Rise over run. Okay, so once we identify 2 points that we want to find the slope or the average rate of change, we're just going to use rise over run. And again, like we talked about Friday, we look at our graphs, we read them left to right. So at the left point, how much are we going to rise to get from the left point to the right point? How many units did we rise? Yes, sir? 3 units. Do you guys agree? Okay. I have a problem because sometimes people count their starting point, but you don't count until you move. So we go up 1, 2, 3. And since we went up 3, I'm going to write +3 because direction here does play an important role on whether our average rate of change is positive or negative. And now to get to the next point, are we going to go left or right? Say it. Right. Okay. So we're going to go right. And since we're moving right, is that a positive or a negative direction? Positive. So we move right how many units? Fabulous. So my slope, now slope is written M. We use the term M. So M equals, what's the slope or the average rate of change between those 2 points? +3 over +2. So our slope is 3/2. That's all you got to do. So when you're given a graph, it's actually a little bit easier once you get the hang of it. Any questions yet? No? Okay, so now looking at the next point, we're looking at the interval from 0 to 3. Now again, we read left to right. So those numbers are talking about our x values. So when x is 0 to when x is 3. Now, how is this one different? It's definitely different from the last one. Crystal? It's negative. It's definitely negative. To go from left to right, we're going to have to go down to get to the next point. So that's what I'm saying. The direction, if you're going in a positive or negative direction, make sure you use that information. Okay, so let's look at this one. Go ahead and try on your own. How many units from the left point to the right point? How many units are we actually going down? Chris, how many units are we going down? And again, since we're going down, I'm going to write -7. Is everybody okay with that? And now how many units are we going to be moving left or right? Nick? Right, so how many units are we moving right? 3 units. 1, 2, 3. So our slope or our average rate of change is -7/3. Make sure you do not forget any positives or negatives. Okay, because that's, again, our average rate of change. Are we increasing or are we decreasing amongst that interval? So that's a big part of it. So far, so good? Okay. Yes? What if it went straight down? Fabulous question. If you have a perfectly vertical line, that slope is what we like to call undefined. Okay, so that has a slope that's undefined. You won't have a real world problem like that. You won't be given one. Now, what would the slope be of a horizontal line? 0. Because you don't go up, but we still go over. So it's when a flat line, a horizontal line, that's 0, but a vertical line is undefined. And we'll talk about that more later, but great question. All right, so for the next one, we actually have a real world scenario. And we're given 2 different types of data set. I'm given something that's a graphical representation, and I'm given something that's in a table. So we have a lot of information to look at here. We are talking about 2 runners running the 400-meter hurdles race. If you don't know what the hurdles are, that's the one when they're running the track and they jump over those like metal/plastic things. Yes, they look like barricades. Oh, yes, sometimes they're actual barricades. That's scary. When you run in high school, they're ones that if you accidentally catch it, it'll go down. So, you know, hopefully you don't eat dirt because that stinks. All right, so first question. Which runner has a faster average speed for the first 9 seconds? So again, this is why we started off last week analyzing our graphs. For the first 9 seconds, where are the seconds represented? Yes, sir. On the left column. Okay, so in our table, they're on the left. Where are they on our graph? Yes. The x-axis. Fabulous. All right, and then we're on our y-axis. We have our distance. And notice in our table, we don't just have an x and a y. We have 2 different y's because we're comparing 2 people. We have 2 different runners running the hurdles at the same time. So for the first 9 seconds, it says which runner has a faster average speed. How are we going to do that? Faster average speed. If we look at the table, I see that runner A in the first 9 seconds runs from 0 to 120 meters. But runner B also runs from 0 to 120 meters. So who's got the faster speed? The faster average speed. Yeah. Who? Neither. Why? What do you mean neither? They're the same. So from 0 to 9 seconds, they have the same average speed. Now, when we have specific numbers like this, we actually have a formula that we can use for slope. It's y2 minus y1 over x2 minus x1. And this does relate to rise over run because the rise is the change in our y's over the run, which is the change in our x's. And we show that change by subtracting. Now, those little subscripts, don't get nervous about those. That's just telling us that the order that we subtract them is important. So whichever y value we start with, we must start with the same corresponding x value when we subtract. If not, you end up with positives when you're supposed to have negatives or negatives when you're supposed to have positives. So it will affect your answer. So 0 to 9 seconds, they have the same average speed. So our second left side question says, which runner has a faster average speed from 9 to 20 seconds? So now we're talking about 9 to 20 seconds. Now we have some different stuff happening. And if we look at our graph, from 9 to 20 seconds, we can see how they actually differ a little bit. And there's no need to approximate because we have the actual values in our table. So let's say we start looking at runner A. If we go look at runner A, they are 9 120 and 20 168. So, whoops. So 9 120 and 20 168. So I want to find the average rate of change or the average speed of runner A. So what I like to do is start by underlining the y values. So which ones are my y values? So you should be looking x, y, so 120 and 168. So do you see a way that looks a little bit nicer to subtract these? So that's how I want you to subtract them. So I'm looking and I'm like, well, I want to take 120 from 168 because that looks nicer. So if I do 168 minus 120, I must subtract 20 minus 9. Does that make sense to you guys? Whichever y coordinate you start with, you have to start with the same x coordinate. So what is 100? Do we have somebody with a calculator? So what's 168 minus, do you have a question? Oh, what's 168 minus 120? So we got 48 divided by 11. So, calculator people. What's our average speed for runner A? We'll just round to the nearest hundredth. Mm-hmm. 4.36 meters per second. Because we are talking speed. Because remember, our y's are talking about the meters and our x's are talking about seconds. So 4.36 meters per second. Does that make sense? All right. So I want you guys to pause the video and find the average speed of runner B. You're going to have to pick back up in video 2.